everyone. Today we're going to talk about experimental design. And in food science, the design of deliberate experiments is actually quite critical. Oftentimes we think of mad scientists just pouring things together, or that chef who just improvises and randomly mixes different ingredients together to come up with a great new food product. Well, that's lovely in principle, but what we need as food scientists to do is have a very deliberate approach to solving problems and a repeatable approach so that we know that when we're seeing an effect and we come up with a desirable outcome, that we're able to repeat that and able to get consistently similar results. So this is what experimental design is all about. So at the end of this video, you'll be able to think and discuss how deliberately we use experimental design in food product development. You'll be able to come up with some good hypotheses for food problems, think about controlled treatments in experiments, and think of the different types of controlled treatments and how they're used. We're also going to talk about discussing setting up treatments in different linear and matrix forms, and identify and control variables within experiments. And then last but not least, we'll think about qualitative and quantitative observations used in food experiments. So why do we care? Again, as I mentioned before, we need to define the activities that we're doing for food product development and in experimental research with food science, so that we know when we are seeing an effect and we can define causality for that effect. We know that doing a certain step caused the impact that we're seeing and the outcome that we're seeing. So we want to also make sure that we're controlling for all sorts of variables. Because again, different things in the environment around us as we're doing our experiment can impact on the experimental outcomes, and those can then skew what we're observing in our experiment. Not every variable we can control, but we want to be aware of what's impacting our experiments. Last but not least, thinking about hypotheses. Again, a hypothesis is a question that using an experiment you can either prove or disprove. You likely have studied the scientific method at some point if you've ever studied science before. And really, the scientific method is just about having a deliberate process about asking questions and coming up with responses. So we're asking that question, doing some background research to know what's been done before and what possible solutions are out there. We'll form a hypothesis. Again, that question that we can either prove or disprove our experiment. We'll go ahead and do some sort of experimental work, do an analysis, and either accept or reject our hypothesis and communicate what we found. If our hypothesis didn't work, then sometimes we got to circle back and do another experiment. But again, when we have a really good hypothesis and we've controlled for our treatments and variables, we're going to be able to hone in much more acutely and be able to find that next experiment. So again, hypothesis. It's a question that you can design an experiment to test. So for example, using a food-based example, let's say I have bread. Maybe I work for a major bakery and we want to enhance the shelf life of bread. Right now, most bakeries in Canada are using calcium propionate as a shelf life extender, and perhaps ingredient supply company has come out with a new ingredient that's has the ability of having a natural claim. Maybe it can be labeled as a spice. Who knows? I'm just giving a hypothetical here, but let's think about what our hypothesis could be. The hypothesis could be, will the addition of this new ingredient increase the shelf life compared to untreated bread and compared to the chemical alternative, calcium propionate? Note, we have those two other comparators in there, compared to untreated bread and compared to the chemical alternative. Thinking back to our pre-experimental design mindset, I could be that chef and I could just say, well, you know what, let's go in and bake some bread with this new ingredient. But unless I had that ability to compare directly, then I don't know if that new ingredient is giving me a better outcome or not. as compared to the previous treatments that we've been doing. Anecdotes are lovely, except they're not very useful to be able to go and improve your point, and having these other aspects of the untreated bread and the chemical alternative in there as comparisons is useful. So let's do a couple more quick examples here. If we were looking at doing French fries better than the classical par fry and fry methods, you could say, if we use this pre-dip treatment, our texture will improve as compared to the par fry and fry. Or freezing in between par fry and fry will improve the texture. And of course, our basis of comparison is the historical method. Perhaps it's browning and dried fruit. This graphic down here is going to give a good example. We have water only with vitamin C and untreated. So we have, and we'll talk about this in a moment, a negative control, positive control, and some other, we're looking at all of these variables that could be impacting. Perhaps it's the temperature and time to make perfect grilled sausage. So our hypothesis could be that maybe there are two sets of treatments that we're looking at here. We're looking at time and we're looking at temperature. Perhaps you have a certain range that cooking in temperatures between 350 and 450 Fahrenheit for 10 to 12 minutes gives the optimal sausage. We have sometimes the opportunity of having multi-dimensional experiments, and it's possible to design hypotheses for this. So within our experiment, we have to think about an orderly procedure, something that we can document and go about repeating to be able to test those circumstances. So again, depending on the type of experiment, you may need to have a positive control or a negative control. Now, not all experiments have all of this, but especially when there's the aspect of comparison involved, it is very important to try and identify appropriate positive and negative controls. And then, of course, you've got your test groups or treatment groups as the next part of your experiment. So again, a negative control gets no treatment at all. Going back to our if we are drying fruit, if our negative control would be just take the fruit, slice it, and dry it. No treatment at all. Positive control is going to get a treatment that we've already defined and we know it works in a very specific way. So going back to our dried fruit, dipping our fruit in a water and ascorbic acid solution will reduce the amount of enzymatic browning that occurs on our fruit. And this has been established in the scientific literature and in just popular knowledge within culinary circles as well. But then perhaps we have a new treatment group. Maybe a food company has come out with a new functional ingredient that has a clean label attribute, or perhaps they have come up with some sort of physical process like high pressure processing or ohmic heating that doesn't require any ingredient labeling. Perhaps that's the test group. That is where we are going to get the treatment that we want to investigate and be able to compare it against our negative and positive controls. So we just walked through the example relative to dried fruit. Perhaps you can take some time now and think about what would be appropriate controls for making French fries or grilling sausage. I'm going to carry on here. Oh, actually I did this for you. So again, our negative control in our dried fruit could be no treatment. Our positive control could be ascorbic acid dip. And the treatments could be new ingredient dip at different levels. So for example, 100 milligrams per liter, 200 milligrams per liter. Again, this would be relative to the Division 16 and list of incorporation for the levels of ingredient, or perhaps from recommendations from the manufacturer. Going back down to our temperature and time to make our perfect grilled sausage, this was a little harder to define. What is our negative control? But perhaps we have a positive control. Like, is your negative control, going back to this one, is it let's just not cook the sausage at all? I don't think that's necessarily appropriate. Not every experiment has clearly defined positive and negative controls. But perhaps maybe our sausage company has been putting out there recommendations on the consumer package that 350 Fahrenheit until internal temperature hits 74 degrees Celsius is the recommended format. Now, we can do our treatments in a matrix format, and setting up a little grid like this is very useful, where you can then see that you have two different directions that your treatments are going in. And then you'd have a sausage, 5 minutes at 350, 5 minutes at 375, 5 minutes at 4. And this is just an example. You would be modifying this relative to the type of product that you have and the different treatments. But it is possible to do 2 or more treatments at the same time if you organize yourself properly. Then there are variables. These are factors that change in the test group as compared to the control. So it is ideal to only change one variable at a time. Going back to this matrix here, we can organize it so that we are managing those variables. So again, thinking about it, preventing browning in dried fruit, are we going in a stepwise approach so that we're not all of a sudden going from let's try the fruit using ohmic heating to see if that reduces browning to let's try using banana peel extract. We're not going to leap around with all sorts of random ideas. We're going to go one variable at a time so that we can hone in on what effects we're seeing. Again, temperature and time to make that perfect grilled sausage. Perhaps we're going to focus on one temperature setting at a time so that we are not, again, leaping all over the place. These matrix-based experiments can become very, very large very quickly. So watch where your variables are and how you're managing them. Then we also have external variables that could be modifying the situation. So what else could we be thinking about? In the case of the dried fruit, what's the age of the fruit at the starting point? Do we have some apples that are freshly picked and some apples that have been in storage for a period of time? Have they all been treated the same way? Dip treatment. Let's say, for example, is the drip treatment being prepared fresh immediately prior to use? Or do we see an effect of an extended period of use? Variety of apple, thickness of fruit profile. All of these become variables that we need to think about when managing all of our different treatments. In terms of the temperature and time to make that perfect grilled sausage, we're looking at the temperature of the sausage from start. We don't want to have some sausages starting from frozen and some starting at room temperature. We need to have them all starting at the same relative temperature. Perhaps the diffusivity characteristic. So we know that the diffusivity of heat through fat is different than it is through water or protein. So we need to make sure that our sausage as a whole is very uniform. We can't compare a hot dog to a salami, for example. These each have different compositional characteristics. Also the diameter or thickness of that product. The thermal flux from the heating device. So for example, everyone knows that on most heating devices there are hot spots and cool spots where things are more prone to burn, and the flux of heat from those different spots needs to be controlled for. And so we'll have a different video about statistical repeats and repeatability of experiments. Watch for that video. Last but not least, we're going to think a little bit about the observations that we're going to make in our experiment. And so what are the measures that we're using to identify the effectiveness of our treatments as compared to our controls? And this is the fun of food science, in that we come from a tradition of culinary where taste and appearance and organoleptic quality is really quite important. And so those are what are called qualitative measures, and they're descriptions, usually not using numbers, whereas quantitative things are things that we can measure in numbers, such as temperature, thickness, shear, viscosity. These can be measured, and some things that we think of as qualitative, such as color, can be converted into quantitative measures using colorimetry or spectrophotometry. There are some ways that we can move back and forth between these two. Now, the challenge with food science is that oftentimes, as food scientists, we say, well, quantitative is better. Quantitative is where things are at. But I want to step outside of that bias and say, you know what? There's many times within organizations where qualitative measures are extremely practical, extremely cost effective, and very versatile for individuals to be using. And so well-designed qualitative measures can be extremely effective for identifying the outcomes of an experiment. So here's a good example. Let's do one together, and then we'll wrap this video up. Let's say we've got that bread shelf life, and bread goes moldy. We know consumers want clean label products, so we're thinking in a problem-solving mindset. How can we come up with a clean label bread? Oftentimes we go out to those trade shows, or we get the industry trade journals, and we identify new ingredient technologies that are out there. So let's say, what's our hypothesis? What's the experiment we want to prove? So in this case, it may very well be that addition of the new ingredient is as good or better than the use of that old chemical ingredient. We were using calcium propionate. Then let's remind ourselves what would be relevant controls. So in the case of bread, we may very well want to have bread with no added antimicrobial treatment. So just a negative control bread. Then we may be wanting to put bread with the historical positive control, bread with calcium propionate. Then bread with our new treatment, so the new ingredient. And again, oftentimes I get questions from students and industry saying, if I'm designing an experiment, how much treatment should I be using? In many cases, and that ingredient supplier would have a recommendation of usage level that would be available in the technical specification of the product. In other cases, there may be a regulatory limit that has been published by Codex Alimentarius or Division 16 of the Food and Drugs Regulation in Canada. And so you can go from there and work backwards from a maximum level. So let's say new ingredient, I don't know, rosmarinic acid. You can use it at GMP. Maybe the specification says use it at 0.2% formulation. So perhaps you want to say 0.2, and we'll go, I don't know, 0.02, 0.1, 0.2, 0.3. You can define an appropriate treatment level relative to the cost and the impact that you believe you will see. Last but not least, what would be some variables that we need to worry about? Obviously, we need to think about the age of the flour, making sure that the experiment is being done in a set replicate so that we're not using one batch of flour for one batch of bread and a different batch of flour for a different batch of bread. Let's say one batch of bread had a plate count background with a lot of mold in it. We want to make sure that that's not impacting on the results that we're seeing. Maybe the weather on the day could be important. If it's really rainy and there's high humidity, there could be, or perhaps windy, there could be a high level of background spores in the air. Maybe you don't want to be doing it on the day that they're changing off the HEPA filters or the filtration from an environmental management perspective. Think about the different variables that could be involved. And last but not least, what would be relevant observations? So in the case of moldy bread, you could be sending it out and doing total plate counts and total yeast and molds, but most consumers are not doing that relative to deciding when to throw out their loaf of bread. The mold in bread is quite unappealing, but in general, there's a background of total yeast and mold that's found in most bread products because of the presence of Saccharomyces yeast. You could just score it based off of the appearance of visual mold, and that is a rather fast and furious bootstrapping method that would quickly hone in on whether your treatment was working well or not, and be a very minimal cost. So let's see how we did here. So our hypothesis, adding the new ingredient will give shelf life as long as the chemical additive used before. Our negative, no additive. Positive, using chemical additives such as calcium propionate. Variables, add the new ingredient at different measured levels. And as we mentioned, these levels are going to be relative to the regulatory levels recommended in your jurisdiction, Division 16, Food and Drugs Regulation in Canada. Last but not least, what would be some appropriate observations? You could do qualitative. Observe for presence of mold using positive or negative checks over time. So you could be checking this every day for 14 days or whatever is relevant to the product. Organoleptic, doing some taste testing to ensure fresh taste. And again, there's sensory analysis classes where you could identify appropriate measures for that. Or it could be quantitative, enumerating total yeast and mold counts, or doing quantitative, let's say, texture analysis. How much shear force is necessary to tear that bread? If reducing staling is part of the chemical additives attribute. So there's a good example of how we're doing some experimental design in food products, and again, using a very deliberate approach to thinking through the minor details for successful design.